Okay, so we've learned about Faraday's law, which says that a changing magnetic field causes an electric field. We wrote this. Okay, so it ends up that we have a very similar rule or similar relationship between the electric field and the magnetic field, that a changing electric field causes a magnetic field in a very similar way. The only thing is there's a missing minus sign. And we have a couple constants in there. Okay, so this constant mu naught is related to the constant that determines how much magnetic field is produced for a certain current. Okay, just like this constant epsilon naught is how much electric field there is produced for a certain amount of charge. Okay, but the form is very similar. The magnetic field wraps around the changing electric field, just like the electric field wrapped around the changing magnetic field. Now, there's an interesting thing that becomes possible because of this. You imagine if you started with a changing electric field. Well, that would produce a changing magnetic field, but that changing magnetic field would produce a changing electric field, which in turn would make a changing magnetic field. So we have this infinite chain possible. Mathematically, what we end up with is what we call electromagnetic waves, or EM waves for short. The simplest example is represented here. What we have is a depiction of this, sort of the simplest electromagnetic wave. So this, you have to kind of imagine in 3D. So there's an electric field oscillating in this direction. There's a magnetic field oscillating, if you will, in the vertical direction. So you have to imagine 3D. So the electric field is going in and out. The magnetic field is going up and down. And then the wave is propagating this way. So electric field, magnetic field, and the wave propagates perpendicular to both of them. This is characteristic of electromagnetic waves. The fields are perpendicular to each other, and the velocity is perpendicular to those two. Okay, so this is a sinusoidal wave, which is a common type. Now, the interesting thing about these waves, which is just a mathematical property of these two equations. So this is just straight math. If you try to find what kind of wave satisfies these two equations, see they're coupled, right? If this magnetic field plugs into that one, that electric field plugs into this. So the two are coupled. The two equations are coupled. And so only certain things are possible. What we find is if you study, this is one possibility here. What you find is that the speed of the wave is related to those two constants. And if these two constants are well-known constants that's determined by measuring forces and distances and things like that, and currents. So they have some already predetermined values, but you find that if you do multiply them and take the square root and invert it, you get this very high number, 3 times 10 to the 8th. This is approximate. It's known to very many decimal places. So 3 times 10 to the 8th meters per second, which is coincidentally the speed of light, which we use the symbol c to represent the speed of light. Now, when this was first discovered, it was what led to the understanding that light was actually an electromagnetic wave. Up until that point, electric and magnetic fields were understood, light was understood, but it wasn't understood that the two were really the same phenomena. So that's probably the main result of this chapter, that light is an electromagnetic wave. All right, so now we know with light that we experience light as having different colors. So if you imagine sending light through a prism, it breaks it up into the different colors, and then what we understand now is that different colors are associated with different frequencies. So we have a wave that has a frequency and a wavelength. And so the wave is characterized by its frequency or its wavelength. Now, we also know from previous studies of waves that the product of the wavelength and the frequency is the speed at which the wave travels. And for light, it's always traveling with the same speed. So that means we know this side of the equation, that constant. So if we know the frequency, we can figure out the wavelength. And if we know the wavelength, we can figure out the frequency. So this little chart over here to the right gives us all the common waves that we're used to thinking about. So let's just zoom in here. So this is the part we're used to thinking of as light. It's a very short range of the electromagnetic spectrum. And you can see it's expanded out here. And these are the perception of the colors. Okay, so our eyes can see from roughly 400 nanometers in wavelength to 700 nanometers in wavelength. Over on this side of the axis is the frequency. So it is on the order of 10 to the 14th, 10 to the 15th cycles per second. So it's oscillating very rapidly, the light that we can see. If you go higher in frequency, shorter in wavelength, we have the ultraviolet, the part that gives you sunburn. If you go to longer wavelength, we have the infrared, the thing that keeps you warm. If you go even higher in frequency, shorter in wavelength, we have X-rays. Okay, so X-rays, things that you try to figure out if your bones are broken, are actually a form of light. Okay, so our microwaves. So we go down In the other direction, expanding out, we get microwaves, the things you heat up your food, or also the waves that your phone send out. So your cell phone operates in the microwave range. Continuing to look further, we go up to this end, we have gamma rays. These are very high frequency, short wavelength. Look at the scale is on the order of tenths of an angstrom. That's the size of an atom. Okay, and indeed these gamma rays are often produced by interactions at the center of an atom. Okay, now going to longer wavelengths, we get into the range of frequencies that were used to transmit television and radio. Your Wi-Fi router is someplace in here. Okay, we could go, the AM radios are even longer wavelength. And you could keep going longer. There's no theoretical limit to either of these. It's just they stop becoming as common. So, just as a reminder, yeah, well, okay, we'll leave it at that. So just to remember, let's just go through it. So let's say your Wi-Fi router. Let's say it's at 2.4 gigahertz. So the wavelength, this is the frequency, yeah, the number of cycles per second. So we have 3. Okay, so your Wi-Fi router is making waves with a wavelength of roughly 12 centimeters. Now, it's possible to measure the quantity of how much each wavelength of light is being emitted by something. So I went out into the garden with a sensor that the physics department has and looked at some different objects. So this line here gives us how much of each different color. See down at the bottom here, there's all the different colors of light. So from 400 up to about 700 nanometers in wavelength. Okay, so the California poppy emits very little light below 550 nanometers. But then it rises really quickly and then has quite a bit up in this range, which goes from, if you look down here, from the green up to the red. Okay, so that's this guy over here. That's the California poppy. Okay, so we could look at the fig leaf next. That's this guy here. You can see that it has a spike sort of in the green. It has a little bit of everything, but it's got more green. Now that's kind of why we see it as green. The rose, on the other hand, is really very much focused just in this range of the spectrum. So it's just the red. Now this purple flower over here, commonly known as a potato vine, has this interesting shape where it has this blue range, the violet over here on the left. It's got a hole in the green, and then it picks up again at the red. We could look at that same spectrum. Oh, I forgot to mention. In the background here, I have the light coming from the sky. It was sort of a gray day when I took this, so I just pointed the sensor at the clouds, and this is the light that was coming from them. So if we think about the light coming off of the flowers, it's actually because of the illumination of the sun. So what I did in the next graph was graph the ratio of the power of the light coming off the flower to the power of light coming off of the sky. So that sort of normalizes it, and it gets rid of some of these bumps. If you notice in this image here of the sky, there's a lot of these lines in it, okay? This has to do with things that we don't get to talk about. Basically the complexity of the atmosphere and the surface of the sun. Okay, but so these look a little smoother, and it also makes clearer the difference between them, because you don't have superimposed over these guys is the smaller intensity here to begin with. Okay, and there's a natural lump here in the middle because of the illumination of the sky. So this is the same graph really, but it makes a little clearer the difference between the different flowers and the fig leaf. Now, our eyes are not actually as clever as this sensor that I use to measure this. We're not actually able to sense every color distinctly. Our eyes have, as you probably know, are built with 4 different kinds of receptors. One of them is just sensitive to all light. It can't really tell the difference between different colors. And then there's 3 other light receptors which are sensitive to different ranges. So this picture here indicates the range that each receptor is sensitive to. So this guy over here is just sensitive to this range, and it's more sensitive here in the center than it is out there. So if you just had that kind of sensor in your eye, it would see darkness if there was light up here in the red. You wouldn't see it at all. Sort of like if somebody shines infrared on you, like your TV remote is shining infrared light out of it, you don't see it. If it could be a completely dark room, you put on the infrared light in your remote control and you don't see flashes of light out of it because your eyes aren't sensitive to it. But it doesn't mean it's not there because we don't see it. So if you were just at this receptor, you'd only be able to see light down there. Whereas if you had this one here, you'd see light over this range, preferentially in here. Okay. So our brain sorts out this information. You can see they overlap a lot, but still it's pretty good at sorting out, well, if it's in a certain range down here, so you have a light here, it sort of activates this one a certain amount, this one a different amount, and this one very little. And then your brain says, okay, that's got to be green. All right. But it's easily tricked. In fact, your computer monitor tricks you quite a bit into seeing things that aren't actually there just by stimulating your cells, those 3 different kinds of cells, in a characteristic way that makes your brain think of something in particular. So our vision sees many different combinations of colors as the same color. There are some people that have a fourth color receptor that can see colors that we don't. Okay, unfortunately it's a very interesting subject, but we can't go into it more. So let's talk quickly about how we get these waves going in the first place. So maybe one of the simplest ones is you just imagine a dipole. But there's a current running here that's increasing that charge difference from the ends. Now we know this dipole will create an electric field, and the current will create a magnetic field. I'm only going to draw it in this plane, so the magnetic field we know circles around that current. And the electric field is also coming out towards us too, but we're just drawing it in the plane. So you can see this has that structure we were talking about for the electromagnetic waves, that the electric and magnetic fields at this point are perpendicular to each other. And indeed, if this current is oscillating, a little bit later those directions will flip. So in the end, we end up with a wave coming out of this thing. Moving outward from the center. That's about all we're going to do with that. It's just a nice picture to go along with what's happening here. We don't really get to go into the details. Okay, but this take from this, the idea is that an oscillating charge distribution will create electromagnetic waves. It doesn't really matter what the shape is. If it oscillates, it's probably going to make some waves. This particular pattern actually is not so uncommon. It's actually the source of what we call atomic spectra. So atoms, individual atoms, have the ability to oscillate. So you can think of it as the electron cloud vibrating. And the thing is that the vibrations are at very characteristic frequencies. So these are the spectrum of atomic sodium and neon. So it's a gas of sodium and a gas of neon. And you can see the basic color going over the whole thing is just a reference. The actual light being emitted is these narrow bars here. Each of those bars correspond to a different frequency, a different wavelength. And the atom can only oscillate at certain frequencies. Okay, so each of these bars is like a different mode for the atom. It's actually transitions, but we won't be able to go into the details at this point. Suffice it to say, if you look at these two different spectra, there's the light coming off of sodium and the light coming off of neon, they have similarities, but they're also different. And so this is one of the ways that we identify different elements is by looking at the spectrum, sort of like a fingerprint. These are the lines of the fingerprint. And so we can identify what the material is by the spectrum that it gives off. You can see, actually I chose these two particular ones because we use both of these gases to make lights. So many of the street lights are the sodium vapor, and it has sort of a characteristic orange color that you've probably noticed. And it's because there is a predominance of this red bars up here. There is some down here in the blue that balances out. Whereas in the neon, which you know a neon sign is very red, you can see that these are all very bright. There are blue lines and green lines, but they're dim in comparison. So the overall redness of a neon sign is because of this predominance of lines up here in the red and yellow. So now let's talk a little bit about the energy density, which we already discussed before. So if you remember, when we talked about capacitors, we said that the energy density was 1/2 epsilon naught times the electric field strength squared. Now it ends up being the same form for a magnetic field. But again, we have the other constant in there, this mu naught. Okay. Now, for a wave, let's write out what a wave, a sinusoidal wave would be. We'd have an electric field, which has an amplitude where k is 2 pi over the wavelength, omega is 2 pi over the period, or 2 pi times f. And similarly, the magnetic field, okay, now we know that these are perpendicular to each other. So then this is going back to, this is one of the mathematical solutions to the coupled equations. Okay, so this is a wave moving in the z direction. The electric field would actually be in the x direction, and the magnetic field would be in the y direction. Okay, but we're just going to talk about the magnitudes. Now, another thing that comes out of solving that equation is that you can't just take any amplitude for E naught and B naught. In fact, they have to be related. So the amplitude of the magnetic field is the amplitude of the electric field divided by the speed of light. Now, if we look at what that tells us, about the average energy density, we know that those averages end up being half. If you think about, if you have the square of a sine wave or a cosine wave, when you square it, you get something with twice the frequency, and it goes between 0 and 1, so the average is a half. Okay, so we could write this. You take out those two, multiply the halves, take out epsilon naught, and then E0 squared. So this would be 1 plus that seems like a weird thing to do. Okay, so why did I do that? Well, the reason is that the magnetic field or the electric field magnitudes is just 1 over c. Okay? So that simplifies this. But let's do it later. But if you remember, c was actually 1 over the root of that. So that means that 1 over c squared is mu naught epsilon naught. So all of this is just 1. So in the end, we can get the energy density by just taking the magnitude, the average energy density, as just the magnitude of the electric field squared, the maximum electric field strength squared, times epsilon naught times a half. Very nice result. Okay, it stems basically from this, and this is just comes out of nowhere for you because we didn't solve the equation. Okay, but this is always ends up being true for electromagnetic waves. All right. Now, there's an energy density in space, but unlike the capacitor, that energy is moving. The wave is moving. So if you think in a small time dt, this block of energy here, so there's a volume of energy, so that, remember that this little u is the energy per volume. So if we think about the energy contained in this block, it will move an amount c delta t in a time dt. Okay, so the energy the energy in this pink volume here is the energy density times the volume. Now that volume is the area times the length of the box. So that allows us to write out what we call the intensity. We use the symbol I, but it's defined to be the power divided by the area. So power is energy per time. So that's the energy per time going through that surface A divided by the area. And if you look at what we get when we do that, divide both sides by A delta T, we just get the speed of light times the energy density. Okay, so it's a super simple result. The intensity is the intensity, power per area, so number of watts, the energy per time per area, is just the speed of light times the energy density. Okay, and the energy density we know we could write in terms of electric field strength. Okay, so for example, sunlight is something like 1,000 watts per square meter. That's the intensity at the surface of the Earth. Okay, so we often measure light in terms of intensity because it's spread out, so it's good to think about the amount per area. Okay, the other thing is that, which is less obvious, is that light has momentum. So again, if you think of this beam of light here moving along, it's a something and it's moving, so maybe it has momentum. And indeed, we find that the momentum carried by a volume of light is actually equal to the energy that that light has divided by c. In some sense, the energy and momentum are kind of like the same thing. Okay, you just have to scale it by the factor c. Being careful here with this equation, that E is the energy, not the electric field strength. Now, I want you to consider now this. Now, what was this average energy density? Well, that was the intensity divided by the speed of light. We kind of just undid this equation, this result here. Now let's write out what that is again. What was the intensity? It was the energy per time divided by the area. We have to keep that one over C. Now we can put this inside. So this is now using our result that the momentum is the energy divided by the speed of light. We can see that this is just the rate of change of the momentum with time divided by the area. Okay, why do we care about that? The reason is, let's go back to Newton's second law. That's how we normally write it. It's not how Newton wrote it. He wrote it like this. Nope, didn't write it like that. He wrote it like this. Okay, he thought of mv as the motion. Didn't think, not, of course he knew what velocity was, but he thought of that as the motion. So what we call momentum now. So he wrote the second law this way. The force was the rate of change of the momentum. And look what we have up here, the rate of change of the momentum. Okay, so now think about this. Suppose you have a laser, and it's creating this beam of light. Here's your laser. Okay, and it's got a beam of light coming out. There's now momentum. So by the third law, if this has momentum, it's spitting these things out. There must be a recoil force here, which is equal to the rate at which that momentum is changing. So how much momentum you're creating per second. The same thing happens over here. If this thing hits this plate, it's absorbing. The light had momentum, all of a sudden it doesn't. Something must have been pushing back on it. So this would also feel a recoil force like this because it must have pushed this way on the light. Okay, so it's really interesting, but this thing is the force per area. So this is called, it's a pressure. It's called the radiation pressure. So it's kind of interesting. What this thing it's just the energy density, but it's also the radiation pressure, which is kind of nice. Things kind of cancel out. This radiation pressure is really small, basically because we're dividing by the speed of light in here. So the pressure ends up being small in general. But it's not zero. In fact, there's serious propositions to use what they call solar sails to move spacecraft. So you put up a big sheet of aluminum foil or mylar or something that's reflective and catch sunlight, and that sunlight pushes on you. You can see over here, that the force on this sheet was in the direction the light had been going before it hit. In fact, if it's reflective, you have the momentum coming in, but also if it goes back out afterwards, you've got the absorption, but also the re-emission, and both of those cause a force to the right, so it doubles the amount of force. We could do another example. So go back to the laser. Suppose this is a laser pointer. And so it's a 3 milliwatt laser pointer. And you want to know, well, how hard do you have to push on the laser to keep it from pushing backwards when it shoots out the beam? So the force should be the pressure times the area. Yeah. So that will be energy density times the area. Now the energy density is the intensity over C. Now the intensity times the area is actually, think what's intensity? Energy per time per area. So if we multiply by the area, that's the energy per time, or the power. Unfortunately, you usually use this P for power also. Here it means pressure, so I don't want to write P. But that's the 3 milliwatts. So this gives us 10 to the minus 11 newtons. So it's very small. You're not going to notice that. All right, so one more thing we want to talk about, and that is wireless communication. We're so accustomed to this, we're surrounded by it all the time now. We have small digital devices talking to each other all over the place. So your phone talking to the cell phone towers, and your computer talking to your Wi-Fi router. So this is all done wirelessly because it's kind of more convenient. So the idea is very simple. You have an antenna someplace. It's actually almost always something like a dipole antenna. So like we showed before, and it creates waves. Then you have another antenna someplace else which picks it up, often the same configuration. Now, the thing is that a wave in itself, if you just sent a constant wave like we showed at the beginning, it wouldn't really carry any information. And the point of sending the wave is to communicate, and communication contains information. So let's suppose, for example, that you want to send the letter E. So you're typing a text message and you want to send the letter E. So pretty much the entire world has agreed that the letter E is encoded by sending in a binary way. So you send a 0, then a 1, then a 1, then a 0, then a 0, then a 1, then a 0, then a 1. Okay, so if we look at this chart here, we have 0, 1, 1, 0, 0, 1, 0, 1. Okay, so that's the signal we would like to send. And there's many ways to do this. So you can't just send a constant wave because that just says I'm on. So one way is just to turn it off and on. So you set the 0 to be when the signal is off. Okay, and then you turn it on, leave it on, turn it off for 2, turn it on for 1, off, and then back on. Okay, so that's called an amplitude shift key. Okay, so that's one method. Another method would be to send 2 different frequencies. So we have a high frequency and a low frequency, and it doesn't really matter which way you go, but the idea is that you map this one frequency to a 0 and another frequency to a 1, and you go back and forth between those 2 frequencies. Another one is called, so that's a frequency shift key, and another one would be a phase shift key. So this is a little less obvious, but it's like, where in the cycle are you? So you can see this one, you're starting and you're about to go up, and then you go down. Whereas in this one, you're starting at the 0 and then you go down first. Okay, so it's a different phase. You could also start at the top and go down. So there's different kinds of phase shift keys, but this is a very simple one where it's just up or down at the beginning. So again, you can see, start here, it's up, down, down, up, up, down, up, down. So again, of course, the receiver has to be able to sort that out at the other end and decode it. But we're pretty good at measuring both the frequency and the phase. In fact, it's possible to combine these two, or combine the amplitude. Okay, and advances in rapidity of sending signals has to do with how well you can decode those same things. Just for reference, this is a T, different signal. Okay, so let's do a quick review. We defined a few things. We reinitiated our understanding of energy density. So it's the energy per volume. For light, electromagnetic waves, we're almost always interested in the average energy because it's oscillating. What we want to know is overall what the energy is. And we talked about the intensity, which is the amount of energy per time per area. And then the radiation pressure, which is the force per area. We had a few relationships between them that we could write the energy density in terms of the electric field magnitude. And then we had this nice one which gave the intensity in terms of the energy density. And then the nice observation that the radiation pressure was the energy density. Underneath was this more fundamental relationship between the momentum of light and the energy.